Thank you for such nice introduction and for inviting me to this seminar, which I found very interesting and enjoying. And today I will talk about magnetoelastic effects in the antiferromagnetic textures. So last week we heard here at the PETA spin seminar also one very interesting talk about neuromorphic computing given by Supriyo Bandyopadhyay. He claimed inter alia that the strain can be used to control these operations during this computing. And he used for as a basic elements ferromagnets in couple with piezoelectric fields. Here in Mainz, we would like to use antiferromagnets instead, and to find out how we can tune the domain structure in these materials with the strain. So today I will try to convince you that strains affect morphology and dynamics of antiferromagnetic textures, and as vice versa, and as a result, the antiferromagnets could be efficiently manipulated by strains. So in my talk, I will introduce some basic concepts of magnetoelasticity, which are important for the devices with which we work in antiferromagnetic spintronics. And then I will illustrate several magnetoelastic effects like dynamics of the domain walls, switching by non-equilibrium strains, and formation of equilibrium domain structure. So I will start from the concept of magnetoelasticity. If we look at a magnetic material in a paramagnetic state, it can have quite high symmetry like cubic or tetragonal. However, below the transition temperature, the antiferromagnetic, in an antiferromagnetic state, the lattice of the material can be deformed, and corresponding shear strain, which depends on the orientation of the nail vector, is called a spontaneous strain when it's calculated for a homogeneous state. And these spontaneous strains, they fix already chosen direction of the nail vector. They do not change the equilibrium state, homogeneous equilibrium state, but they can strongly affect dynamics. And the point is that usually these strains have relaxation time or characteristic time, which is much slower, much larger than characteristic times of the magnetic dynamics. And once formed during transition point, these strains could be considered as frozen into the lattice. These frozen strains create some additional contribution into the effective anisotropy potential of an antiferromagnet, as we can see in this slide. So initially, without magnetoelasticity, the profile of the magnetic anisotropy is asymmetric and has, as in this case, a tetragonal symmetry and 4 equilibrium states. However, if we take into account magnetoelasticity, so the spontaneous frictions, they deform the profile of the magnetic energy, and then they create effectively one easy axis instead of 2. This phenomena was known for a long time ago, and in the 60s, it was introduced a concept of magnetoelastic gap, which we can observe in the spectrum of magnons or in the spectrum of antiferromagnetic resonance. However, more drastic effects appear when we consider these spontaneous strains in application to multi-domain structure. So if we consider a pure magnetic antiferromagnet without magnetoelastic interaction, then the domain wall in this material appears on top of homogeneous distribution of the magnetic anisotropy profile. And this means that the domain wall can move in this material without additional activation energy. So the domain wall is an excitation which has no activation gap. However, if we take into account magnetostriction, as shown in this slide by the color, then equilibrium domain wall appears on top of the space-dependent potential, anisotropy potential, which chooses different directions of easy axis in a different part of the sample. This means that the shift of such a domain wall from the position given by magnetostriction is related with an increase of energy, because the Néel vectors or spins which are within this rectangular area are pointing in the direction which is not easy direction in this area. This means that in presence of magnetostriction, the domain wall is spin, and then slight excitation of the domain wall, slight shift from equilibrium state, induces oscillations of the domain wall around the equilibrium state with the frequency which scales with the magnetostrictive constant. And as you see from this graph in the left side, this frequency of the domain wall grows with the value of magnetostrictive constant, and this frequency can reach 80% of the antiferromagnetic frequency resonance, so it could be very pronounced, even for very simple geometry. Another interesting effect coming from this frozen striction we can observe in such materials as cobalt oxide or nickel oxide, in which we can find so-called T-domains. These magnetostrictive T-domains are known to have fully different orientations of the magnetic anisotropy axis. So we have three-dimensional picture for the domains. And in this case, for example, magnons propagating from one domain to the other can show the effect of birefringes, which we know from optics. And this can induce also rotation of the polarization plane of magnons. Another effect in these materials can result from the mixing of the oscillations of the domain wall with the frequency of magnons, and induce through parametric downconversion mixing of two modes which in a homogeneous state are always fully independent. This was recently observed in ultra-fast optical experiment by Bossini and others. So now I would like to turn to the other concept, which is also very important for these magnetoelastic effects, and is called incompatibility of strains. So I will illustrate this concept on two very simple examples. First, imagine a magnetic film grown on the substrate, and in a paramagnetic state, the lattices of the magnetic layer and non-magnetic substrates are the same and continuous. However, when the system goes through the Néel point, an antiferromagnetic layer tends to contract in one direction and elongate in the other direction, while the substrate wants to stay as it was. And this conflict of interests induces a so-called incompatibility of strains at the interface, which can be seen as a defect which can lead to the broken continuity of the crystal. Another example of the same phenomenon can be found when we consider conjunctions of two domains with different spontaneous restrictions. So for the arbitrary orientation of the domain wall, the deformation of the domains cannot match properly, and they also introduce a kind of incompatibility of strains. So this was an intuitive picture, but incompatibility in the elasticity theory has a very accurate mathematical definition, as shown here. And it appears in the theory of elasticity with the defects like dislocations or disclinations. And this incompatibility is a source of additional strains in the material, which try to compensate the strain or stress fields created by this defect. And in this sense, incompatibility is very similar to the magnetostatic charges, which we can find in ferromagnetic materials. So the charge is proportional to the divergence of magnetization. Both values have the same mathematical properties. They create long-range fields, and they can be responsible for creation of inhomogeneous structures, domain structures, textures, as I will discuss at the end of this talk. How these incompatibilities can be observed in the experiments, and what consequences of these incompatibilities can we find in our materials. Now I would like to describe you how these incompatibilities can appear as an external fields, even in such far-laying system as electrodes with current. In spintronic experiments, we usually use certain geometries of the electrodes. One of the simplest cases is shown here. And the current which flows through this system has strongly inhomogeneous distribution of density in the center of the device. This inhomogeneous distribution of current density through Joule heating induces inhomogeneous distribution of temperature. And as a result, locally, the system would expand, but the volume expansion should be different in different parts of the sum. And this inhomogeneous volume expansion can induce the strains which will interact and switch antiferromagnetic vector, as I will explain in the next slide. So here you see a cartoon which shows distribution of temperature. So the color shows hot and cold regions, and squares show volume effects which appear in different regions of the sample. And if we look at the interface between hot and cold region, we see that these volumes, the volume deformations, do not match each other. So again, we have a kind of incompatibility, and this incompatibility creates shear strains. So elongation in one direction in the cold region, shown with ellipse, and elongation in the perpendicular direction in the hot region. Such inhomogeneous distribution of shear strains can be seen as an effective field which acts on an antiferromagnet and contributes into the effective magnetic anisotropy. And it is very similar to the effect of the magnetic field, which we know very well for antiferromagnetic material. So in the center of this cross, the total strain created by such strong inhomogeneities sets a preferable direction of the strain, or preferable strain field, which favors this or that orientation of the null vector. And experimentally, we observed this effect in two materials, nickel oxide and cobalt oxide. So here you see the results of the experiments. A black and white contrast shows domains seen by XMLD, and the color code shows a distribution of strains which were induced by certain current geometries in each of the experiments. So you see a correlation between the switching phenomena and current direction. However, to prove this thermo-magneto-elastic mechanism and disentangled it from possible spin torques, which can be also induced by currents, we created a special geometry with a hole in the center. So in these samples, there is no current which flows through the central region of the electrode, but still, due to heating and strain, we see switching in different directions. And of course, such strain induces not only modification of anisotropy potential, but also certain torques which induce switching of the area as shown here by simulations. So you see that we can go from one state to the final state, and this is very similar to what we see in the experiments. And now I came to the last part of my talk, which is related with the description of the domain structure and in antiferromagnets and corresponding technique which can be used to describe it consistently. So the first notion is that the origination of the domain structure in antiferromagnets can be explained by presence of strains and incompatibilities which appear at the interface between the magnetic layer and a non-magnetic substrate. If the antiferromagnetic layer shown in this picture is homogeneous or single domain, then the substrate and magnetic layer would be unhappy because of large incompatibility and corresponding strains. And this unhappiness mathematically is expressed as the contribution, positive contribution into the energy, which scales as a volume of the sample. This energy, which we call distressing energy, is very similar to the magnetization energy in ferromagnets, and it has a very similar origin in the sense that it originates from long-range fields. So in this case, the sample would be happy, this energy would be diminished if the sample will split in many tiny domains with equal probabilities of different domain types. Another effect, which also originates from this incompatibility, is related with the orientation of the domain wall. As we already mentioned, the arbitrary joint of arbitrarily oriented domain wall at the junction of two domains can create incompatibility and corresponding strains, energy of which again scales as a volume of the sample. So if we look at two domains, blue and rose, then for certain directions, for example shown here, the length of the domain in this direction is different for blue and for rose. And this means that we have incompatibility related with this inconsistency of length. And this domain wall will have higher energy. However, if we try other directions, we can find two, in this case, in which the two domains fit each other perfectly. And this should correspond to the minimal energy. So if in a pure magnetic domain wall has no preferable direction in antiferromagnet because there are no demagnetizing fields, in presence of magneto-elastic coupling, we have two preferable directions. And this means that the domain walls will tend to orient along hard directions and to be as flat as possible to avoid energy costs. So here we summarized these two mechanisms, showing a very simple picture of the domain structure, which will minimize energy of the infinite thin film of an antiferromagnet on substrate. So what we see here, we see periodically alternating domains of two types in both directions, separating by the domain walls which follow a hard magnetic axis of the sample. And the size of this domain, of course, depends on the elastic properties of the substrate, antiferromagnetic film, and on the energy of the domain walls and junctions. What do we have in the experiments? Of course, experiments show much more complicated pictures, as you can see here in these slides. These images were done by the group from Nottingham, Peter Hadley is a PI. And the material is a copper manganese arsenide, tetragonal symmetry. So what we can see in the right bottom image, the structure consists of black and white domains, which are distributed more or less equally with equal density. And also, if we look very attentively, we can see that the domain walls follow some preferable directions, and some areas really look like rectangulars, which are predicted by the serie. In the left slide image, we see a cross, so this is not an infinite area. And then the domain structure is different. It consists of mainly on stripes, but again, these stripes have preferable directions, which correlates with orientations of the hard axis, consistent with the predictions of theory. Interestingly, if we apply current pulse to this system, the domain structure changes, absolutely changes. So now we see tiny domains with Arrhenius domain walls and so on. So this means that there are a lot of room for application of this magneto-elastic concept and study of the different domain structures which can appear under external fields like temperature gradients, currents, strains, and so on. For this, of course, we need some mathematical tools, and what we suggest is to use an analog of Micr-a-magnetics. We called it Micr-a-magnetics, and the idea is very simple. For some cases, we can, and if we are interested in equilibrium structures and static pictures, we can integrate out the strains from the energy expressions, and then get a kind of closed expression for distribution of, for arbitrary distribution of the Néel vectors coupled by kernels which have similar properties as the kernels in magnetostatics. So then the question is how to plug in this expression and how to develop new computational technique, because the expressions are more complicated and they contain are based on fourth order terms of antiferromagnetic vectors. But this means that this is an open area, and it could give a new interesting phenomena if we worked with it. So with this I came to the conclusions. So magnetoelastic effects are very important for description of domain wall dynamics and for the equilibrium and non-equilibrium domain structure, and they can define switching between different antiferromagnetic states. And as the last slide, I would like to show all my experimental collaborators, so experimentalists from the University of Nijmegen, Constance, Stockholm University, and of course, fantastic group of Matthias Klaue from Mainz. And I hope that there is room here for other pictures, so maybe someone who listens my talk will join me and collaborate with me on these topics. So thank you for your attention.